Hi, everyone. Today we have Victor Albert. He's a physicist at the National Institute of Standards and Technology and adjunct assistant professor at University of Maryland, College Park. And he works in a wide range of topics in quantum information science and condensed matter. And he has worked on superconducting circuits, molecular physics, and also some some parts of quantum machine learning. Uh, he did his PhD from Yale and then was a postdoc at Caltech prior to joining Maryland. So today he's going to tell us about spin chains, defects, and quantum wires for the quantum double edge. Please go ahead.
Thank you, Arpit. Thanks, everyone, for this opportunity. This has been brewing since maybe 6 months into my postdoc at Caltech, so for about 4 years now. And I want to thank, actually, first off, I'll thank my collaborators later, but I wanted to thank my relatives for helping babysit my child all of last year during COVID when I was finally trying to really wrap this up. So since I have, as Arpit said, around 5 hours, I believe I wanted to spend some extra time motivating and maybe try to go a little bit slower. This motivation is more historical, based on my interest in continuous variable configuration spaces. So instead of thinking about qubits and qudits, as a grad student, I worked at Yale on sort of continuous variable or degrees of freedom characterized by position momentum. The physics there was that of electromagnetic field modes, which was one of the big four. This top left physical setting in which people were and are still building quantum devices and quantum computers. But of course, continuous variable harmonic oscillator configuration spaces have many applications. So it was fun to work on the theory because it had a broad application range. When I got into my postdoc, I discovered with the help of John Preskill that there were more configuration spaces, both discrete and continuous, out there. And I had dug up an actual application of one of these CV configuration spaces to a particular physical system that's not a harmonic oscillator. So I'll describe it in this slide. So the rigid body is this system, and its orientation in space and angular momentum can also be thought of as a pair of conjugate variables analogous to position momentum. Then the rigid body that we can discuss with our experimentalist colleagues without them laughing at us is a molecule. There's been lots of progress in trapping and controlling molecules and trying to stabilize quantum superpositions of molecules, of small triatomic, diatomic molecules. And so as a theorist, it's very interesting and useful to develop some of this quantum math for these types of spaces. It's been, of course, developed in the molecular physics and chemical physics communities, but it hadn't been looked at in too much detail from the quantum information perspective and condensed matter perspective. So this sort of is my motivation for looking at various configuration spaces, namely because there are particular ones, the harmonic oscillator and this rigid body, that are connected to physical systems. But also, again, as a theorist, I like to look at the general case, which is just encompassing, which I'll do today. So just to briefly introduce what this rigid body configuration space is, I'll review first the harmonic oscillator, whose kets are described or are in one-to-one correspondence with points on the real number line. So these are position states that everybody, I hope, is familiar with. And moving on to something that's more related to the rigid body, if you trap a rigid body in 2 dimensions, then it's the same as identifying or imposing periodic boundary conditions on your line, and you get a circle. So both of these configuration spaces can be identified with groups, the reals under addition and the phase group U1. And now, if you want to study this more exotic rigid body, which is here represented by a triatomic molecule in 3D, there you can also associate with the configuration space of a group, but the question here is, what group do you use? Does anybody know off the top of their head who hasn't seen this slide before? Think angular momentum. Well, let's find out. So if I have my triatomic molecule and I start and I want to index all the possible orientations of it, just like an analogy to all the possible positions of a harmonic oscillator, I start with some reference orientation and I rotate it by some angle around some axis, and I get a different orientation. Why do I get a different orientation? Because the molecule is symmetric. It's not symmetric under any SO3 proper special orthogonal rotation. If I do this, if I start with the same reference orientation and do it again by applying a different rotation, I get a different orientation. I get a different one every time. And so I need all elements of SO3 to label all possible orientations of this 3D rigid body. Now, again, I'm using a molecule because this is relevant to quantum mechanics, but you can also use an airplane or a robot arm if you feel so inclined. This applies to all of them. So this is basically the explanation of why you need the group SO3 to label all these orientations. And the extra complication here is that this group is non-abelian as opposed to the reals in the U1 group. And so a lot of my postdoc has focused on dealing with the intricacies of this group, of this configuration space and the structures on top of it, along with applying those structures to relevant problems in error correction and quantum information, quantum matter. So just to wrap up, all of these nice physical examples are examples of configuration spaces, in this case continuous, but in general, we can also sort of shovel in our conventional qubit and qudit spaces into this framework and study all of them at the same time. And this framework is just dealing with configuration spaces that are labeled by elements little g in a group capital G. And capital G can be basically three types of groups. We've kind of highlighted the continuous compact capital G, which is SO3. We've seen the oscillator R. And the third part that I also want to mention that's important for the project that I'll review here in particular is the discrete non-abelian but finite group G, like dihedral group, quaternions, etc. That also is useful for the condensed matter applications. So all of this can be done in one framework, and there's lots of different applications to this that are fairly kind of disconnected, and so far I've been trying to connect them a little bit because the math behind them is kind of the same. So I don't know if I should be proud of this research style, but this is how I've been doing it for the past 4 years. I've just been looking at sort of the structures here and applying them as I go to various problems throughout quantum science. So the first problem that we studied was error correction, and it had to do with encoding in a robust fashion one group space, the superpositions in one group space into multiple, generalizing stabilizer-based error correcting codes for qubits. The second project dealt with encoding a two-level space, so just say Z2 group space, into a space associated with any other group G. In this case, if G is SO3, then you get encoding of a qubit in a molecule. So you obtain sort of generalized versions of codes that did the same thing, but encoded into an oscillator called GKP codes. And more recently, we've been studying now multiple sort of monogamy of entanglement communication protocols with Tomáš Vidic at Caltech, actually, using these group spaces, generalizing a lot of these coset constructions that people use in these cryptographic protocols. And finally, tired of zero-dimensional physics, this is my coming out party to one dimension, still too scared to do two, but going to stick with one for the rest of this talk. And I will study sort of the simplest Hamiltonian that I could think of that one could try to write down for a one-dimensional chain of group spaces. This Hamiltonian is Ising-like, and it turns out that this also has applications to, namely, topological defects and quantum double models. So I guess I'd be happy to field questions as we go. Does anybody have any at this point? Yeah, so feel free to interrupt anytime. So for this project, I want to acknowledge the following people. Jason in particular has been extremely patient meeting with me anytime I basically felt like it or was stuck, which was a lot. And also in particular, Dave, who has a very unique understanding of the world and is also very happy to explain it to anyone who's listening and take the necessary time to do so. So without them, I would have definitely not have been able to do this stuff. So let's now zoom into this condensed matter project, this many body spin chain project, and motivate it a little bit. And the motivation here is topological quantum computation, which holds the promise of computation in an inherently robust fashion using some sort of things called topological defects or zero modes or all sorts of different names for these things. But in general, the objects that one uses to perform operations on a topologically protected subspace can come from 1D subsystems of 2D topologically ordered states. For example, edges, the things that happen on the edge of a system or on a line defect within the body of the system. And such subsystems can inherit some of the topological properties of the 2D parent medium and therefore be used to realize 1D structures that are impossible using plain old bosonic degrees of freedom arranged in a spin chain. So this is useful because these types of properties can be used to perform operations, as I said, on protected states, so namely protected logical gates, topologically protected logical gates. And for many of these, you have to be embedded in a particular topologically ordered phase because otherwise you don't get these extra properties. So this is probably fairly vague because there's been a lot of work on these, and I definitely won't do due diligence here in reviewing all of it. But these 1D subsystems, topological defects, arose initially from Kitaev's famous paper in which he identified a particular 1D system of fermions whose ends harbored Majorana zero modes, which I'll represent by these stars as an example of a topological defect. And so this system can in fact exist in a bona fide 1D fermionic chain, but spin-offs of it, namely the parafermionic spin chains developed by Fendley and a more recent paper on dionic zero modes, do not exist naturally in a 1D medium and do require embedding in a 2D topologically ordered phase. So with the exception of the purely fermionic system, all of these have to be embedded or in some contact with a 2D topologically ordered medium. Another example of such topological defects is occur in lattice models, where in 2D you can embed some sort of, like I said, edges or line defects. And there's been lots of different studies, starting, I think, from Bombin's paper and Bravik-Kitaev and others, studying things within the bulk or on the edge of a system. So both of these types of defects in the zero modes that are harbored by them have been studied from the point of view of a lattice system. However, continuum systems are also just as important to study, because continuum systems is where you make contact with experimentally relevant systems, which are often described by continuum theories. And the continuum theories that we'll focus on here on today will be quantum wires, which I'll describe in a few slides. But just to review the progress here, continuum analogs of Majorana zero modes have been studied and realized before, as well as continuum analogs of the zero modes associated with the parafermionic chains that were developed on the lattice. Now, because these parafermionic zero modes cannot be constructed out of fermions off the bat, because they're not really fermionic, you have to cleverly use some 2D medium, but now in a continuum formulation to obtain these things. And this has been done by Jason and by Gil at Caltech and others, using fractional quantum Hall edge state degrees of freedom. And I'll discuss that later as well. But in any case, I guess for the point of the summary of this slide is that lattice formulations and continuum formulations are both, in some sense, of comparable importance, because the former can be used to understand the algebraic properties of the defects, and the latter are often very relevant in experimental systems, such as fractional quantum Hall and other electronic systems whose 1D sections are described by quantum wires. So any questions on this sort of vague overview slide? Okay. Before I get into our results, I wanted to review the even more prior work or more specific prior work that we've encountered. So the toric code, which can be easily extended to qubits or qnits in this talk, is a topological phase that admits gapped edges, which means it does not have gapless zero modes like a topological insulator. And these gapped edges have been studied and classified, and turns out that defects between them harbor Majorana-like zero modes that can be used to manipulate the ground state subspace of the toric code with open boundary conditions. And I think this was first done by identified by Bravik and Kitaev. But if you basically write down the edge Hamiltonian for the toric code, you will see that it's equivalent to the Ising model once you project out the bulk degrees of freedom, where you basically freeze the bulk in the ground state no bulk excitation subspace, and sort of trace it out. You'll see that the edge is described by an effective edge theory that's equivalent to the Ising model for the Z2 case, and the clock model for the ZN toric code case. So this is something that's been sort of sporadically known throughout the literature, and I've tried to collect all of the relevant references that have mentioned this one way or another. And I'll go over in detail on how to do this procedure. And that's basically on the lattice front, but because the Ising model has very well-defined continuum analogs, there have been continuum versions of these zero modes associated with the Ising model, Jordan-Wigner transformed Ising model, in superconducting and ferromagnetic interfaces of the edges of a fractional quantum Hall. And I mentioned this in the last slide. I want to mention specific papers here. So basically, the point is the toric code has been studied from both the lattice and the continuum perspective fairly well. But generalizations of the toric code to these group spaces that I had motivated this talk with is not as well studied. These generalizations are called quantum double models, and that will be sort of the main focus of this talk. And these admit significantly more complex low energy bulk excitations in the form of anyons, as well as other types of, or as well as other anionic type defects that have been classified from the category theory perspective. And despite, well, because they're more complex, they're also potentially more useful because they offer other ways to store and protect and manipulate quantum information that were just not accessible or possible in the abelian or Zn toric code cases. And there's these papers, for example, have been studying that those new avenues. So in particular, the way that anionic excitations behave when you move them to an edge has been well classified in a series of papers by various authors using category theory. However, what's been done almost to the same level of progress as for the toric code, but maybe not quite, is actually deriving a standalone edge theory and projecting out the bulk degrees of freedom to obtain a strictly 1D spin chain associated with the quantum double edge. Now, this series of papers that I highlight here come fairly close. But so far I haven't seen an explicit, construction that we do, but I could stand corrected maybe sometime in the future. But nevertheless, that aside, whatever that theory is has not been very well studied for the special case of the quantum double models, because the papers to the right there study everything from the point of view of string nets. So specializing to the group case induces a lot of other structures or specific structures to the group that have not really been studied from this point of view. And much less, of course, has the continuum description been studied, because there's no clear-cut lattice description akin to the Ising or clock model. Continuum version of it doesn't exist, of course, as well. And so these continuum analogs of the zero modes that were developed at the superconducting / ferromagnetic interfaces have not been developed, have completely not been developed yet. Now, from another perspective, Monk, Rasmussen, and Borello a few years ago did develop a spin chain that looked and smelled very much like the 1D model that you would expect to happen at the edge of a quantum double model. And they developed sort of this model in their own way, offering another Jordan-Wigner type offering a type of Jordan-Wigner transformation. But because they were developing it from their own perspective, there was no real clear connection to actual quantum double models. And so these three sort of question marks are things that we'll be reconciling explicitly today. Okay, so I really want a question. So I'm going to keep pausing until somebody asks, because I don't want to start getting over everybody's head here. Is everything really crystal clear? So we're trying to generalize basically 1D effective theories of edges of quantum double topological phases from the toric code case to the non-abelian group case. And we're trying to connect this flux ladder spin chain that was developed in separate effort by Monk, Rasmussen, and Borello to quantum doubles, develop continuum descriptions of it, and try to cook up some topological non-abelian defect operators for it. So let me summarize what I just said, maybe a little bit more extended way. So we'll be springboarding off the abelian case on the left here, which is all known in various papers, to the non-abelian case, which is sort of the main thrust of this work. And so to review graphically what we did, We start with the toric code bulk on a disk, and we take the edge of a disk and we apply a stabilizer-based procedure that projects out the bulk degrees of freedom, arriving at an effective 1D theory that you have to think of as being, in proximity to a 2D quantum double or a 2D topologically ordered toric code bulk, but nevertheless the physical Hilbert space is 1D. Now again, I said this was already done, but we'll be doing analogs of this for the non-abelian case. This Ising, or more generally clock model, can be, of course, mapped to a chain of fermion-like parafermions using the Jordan-Wigner mapping developed by Paul Fendley. To connect to the continuum front, one can do another fairly well-known procedure of embedding each unit at a spatial site of the clock model into a U1 or planar rotor degree of freedom, kind of thinking of like the U1 rotor as a pizza and the Zn is cutting up the pizza into n slices. If you do the reverse of this, you embed the Zn into this continuous valued U1 valued rotor, you then can Taylor expand the operators of the rotor because they're written in terms of the Lie algebra of the rotor, and thereby obtain in the continuum limit a field theory of the free boson, which is what a field theory that's called the free boson, thereby obtaining a continuum analog of the Ising model that's well known to describe the Ising clock model's features. And the analog of the Jordan-Wigner mapping in the continuum case is something called bosonization, which converts this free boson into a fermionic model, which I'll call a quantum wire. So this is a set of sort of connections that I wanted to point out that's been done in various corners of the literature for Zn type models, the toric code, the Ising model, the free boson, the quantum wire. Now, in the non-abelian case, what we do is we take a quantum double bulk and we generalize the procedure of projecting out the bulk to obtain a flux ladder. We project the low energy anionic excitations onto this 1D space of the flux ladder and obtain what we call flattened ribbon operators. We use these flattened ribbon operators and construct Jordan-Wigner type operators out of them, obtaining an analog of this parafermion chain for the non-abelian case. We then, and this took me a long time to figure out, but there's a non-abelian version of this embedding that's obvious in retrospect, where you take the non-abelian finite group G and you embed it in a continuous Lie group gamma that contains G as a subgroup. I think this is something that people often refer to as Higgsing. This is sort of the reverse of that. And if you do this embedding, you can then express everything in terms of a Lie algebra, and you can Taylor expand, take the continuum limit, and you get an analog of the free boson field theory, which is called the principal chiral model in the literature. So that's how the flux ladder is connected to has extended to a continuum formulation. And then the principal chiral model with some extra tricks can be recast as a set of coupled quantum wires, generalizing the bosonization procedure using non-abelian bosonization. And we conjecture that just like on the abelian case, the quantum wire will harbor continuum zero modes, parafermionic zero modes. We will conjecture that the non-abelian coupled quantum wires will also contain non-abelian type zero modes that may be associated with these anionic excitations of the quantum double bulk. We do not derive these zero modes, however, but we do, in sort of a separate analysis, test this G to gamma embedding for the bulk. And if we apply this, we test it in the sense that we want to see if it preserves the topological excitations of the lattice model when going into the continuum. And the test actually passes, because when you do this Higgsing type procedure for the bulk of the toric code, you get an abelian gauge theory. When you do it for the quantum double, you get a non-abelian gauge theory associated with the group gamma. And both of those gauge theories have been known since the 90s to admit topological excitations when they are Higgsed to this respective groups Zn and G. So this we're mean, I'm fairly confident this continuum embedding procedure preserves the topological nature and the excitations. And so it's likely that topological defects, non-abelian defects, will exist in the continuum as well. But I want to reiterate that we do not explicitly find them for this non-abelian case. We just set everything up. Okay, so that's sort of the more long-winded summary of what we do.
What about going to the non?
What?
What about going to the non?
Having trouble hearing. You said, what about going to the non-abelian what?
From non-gauge theory to the principal pair model. Can you hear me?
No, not really.
Okay.
Just type it. Okay, so while Arpit types, I'll go over three different things here. So first, we're going to do this explicit procedure, which traces out or gets rid of the bulk degrees of freedom to obtain edge degrees of freedom. Oh, non-abelian gauge theory to PCA. Oh, yeah, there's a glaring connection that's missing. Yeah, good question. I don't know how to do that. The continuum limit part is different for the 1D case than the 2D case. The 2D case is this well-known Kogut-Susskind mapping and Taylor expansion. The 1D case is a different type of Taylor expansion and combination of fields. So good question. Somebody knows this in the abelian case, please speak up. All right, so let's go over this procedure that was developed before for the abelian case. So just to review, a qubit at each point in the lattice admits n position states k kept labeled by elements of Zn or the integers mod with addition mod n. And it admits Pauli operators x and z, where x just shifts you by h, and z spits out a root of unity at each ket. These satisfy a wild commutation relation. And the toric code for qubits can be written in the following way. For the bulk, it consists of four-body operators that are on these crosses or stars or squares and plaquettes here, z and x respectively. And a general edge Hamiltonian for the boundary that I've drawn here can be written in terms of truncated stars and plaquettes at the edge, where the truncated star is just consists of three sites, because the rightmost site has been cut off, and the truncated plaquette consists of just one site, because all the other three have been cut off. Now, this type of Hamiltonian is general. I've kept the parameters C and F here general. Traditionally, people tend to pick either C non-zero or F non-zero so that the edge Hamiltonian consists of only commuting terms, but I want to keep things general, so I'll define the parameters later on and just keep them open for now. So the bulk Hamiltonian terms commute with each other. The edge Hamiltonian terms commute with the bulk Hamiltonian terms, but the edge Hamiltonian terms do not commute with each other. So in general, this system, the total system, does not have to be gapped. So how do we peel off the edge? Well, the first thing we do is we coarse grain the square lattice using a series of local moves that preserve the topological order of the system. And we're going to coarse grain it and mold it into this bicycle shape, this disc-like bicycle shape. So now I've drawn a portion of this bicycle and I've drawn the edge operators on it. So the edge operators are still, the x's still remain three-body terms and the z still remains a one-body term. And the next step we do is we assume that the bulk is in the ground state, and which means that all the bulk plaquettes and stars are in their +1 eigenspace. And those we treat as constraints on the edge Hamiltonian, and we apply them onto the edge Hamiltonian as follows. So first we define what our edge Hilbert space is. So we're going to label it by sites x, where x is roughly corresponding to a spoke in this bicycle wheel. And sans serif font will be used for sites. Yeah.
Sorry, can you hear me?
Sort of, yeah.
Maybe I missed something, but if that boundary while
Still having trouble hearing you, Arpit. Sorry.
um,
Is it just me, or is everybody's also having trouble hearing them? I'm sorry if it's just me.
His audio is not very clear.
Chris, hey. All right. It's not just me. Okay. Well, I guess Arpit, you might have to type it or mess with your microphone a bit. I'll just keep going for a bit.
I
So
actually have a question though.
Go ahead.
So whenever you do the sort of the deformation to this bicycle shape, what's happening to, should I be thinking with like what's happening to the, on the left we have like a surface code. So what's happening to the north and south? Should I be thinking of there as like there being north and south boundaries and something's happening to them whenever we do this, whenever we deform to this bicycle shape?
Yeah, you can think of like a disk.
Okay.
And maybe at the corners of the disk, there'll be truncated plaquettes and stars that have different numbers of X operators and Z operators in them because of the shape of the lattice. But what you want to take away is that it doesn't matter, because I've kept the edge general. The algebra of operators on the edge is the same, no matter what type of lattice edge you do in the physical sense. So these local moves will just change sort of the shape of the operators, but their commutation relations and algebra will remain the same.
Okay, thanks.
It's a bit confusing because people say like, so this is a smooth edge, and they often write only like the Z term, I think, for the smooth edge. And then they have a rough edge where you have the lattice, you don't have a smooth sort of boundary, you have just the ladder type horizontal line sticking out. They call that a rough edge. But the point is you can write down a general edge Hamiltonian of truncated stars and plaquettes on both the smooth edge and the rough edge, and the algebra satisfied by those would be the same. So here, without loss of generality, we're going to be doing a smooth edge. And right, so we have to take care of both the bulk and the boundary operators. So Arpit asks, is there a reason for choosing the boundary X term to be the full vertex operators? Yeah, so so the way I'm doing it is valid for all types of geometries. You just take the plaquettes and stars that don't quite fit, and you put their piece that fits on the edge that you've drawn, on the lattice that you've drawn. So that's the recipe. So here, the plaquette that just not quite fits is the one that has only one side on the lattice that I picked, and the star that doesn't quite fit has 3. But on a rough boundary, the plaquette will have 3 operators and the star will have 1 operator. But again, algebra-wise, it's all the same. Okay, so to have to take care of both the bulk and the edge operators, and I've drawn only the edge operators on the disk, and the bulk operators I've drawn here on the lower right. So for the bicycle shape, the bulk operator turns out to be this single plaquette term that's just a product of X's on all of the spokes. So instead of being a cross, it's this, this thing that covers all of the spokes, just kind of like a really big type cross. And the bulk plaquettes correspond to products of Z operators on the pizza slices of this tire. 2 spokes and a section of tire. And we assume they're all 1. So these are the constraints that we have to put on them to get an effective edge theory. And our edge operators are highlighted here in green. So the X edge operators I've defined to be X superscript X as in spatial position X. And the Z operators on the edge are these single Z's lying on the section of tire. And we're going to apply the bulk constraints to manipulate the Z operator to get a clock model ZZ type coupling in the space, in the physical space labeled by the X indices. So here's how we do that. It's actually pretty simple. You just insert a Z dagger Z, which is identity, to the left and to the right, and then recombine And you see that you can recombine into and get a global plaquette operator sandwiched by z's at the spokes to each side of it. But then you notice that the global plaquette, sorry, this plaquette operator z triangle is just the bulk plaquette, which we've set to 1, so that you can eliminate that by the bulk constraint. And then using the definition of zx that I've defined, you can write the z on the edge z term as a product of z dagger x minus 1 and zx. So in the end, what are we left with? Well, the clock model. The x edge operator is defined to be just a single x on each site, and the edge z operator turns out to be a product of z's on neighboring sites in this new relabeling geometry. And so we can peel that off and get an effective edge theory. So this was done, in the most explicit way this was done is this paper by a few years ago, but again, I know people will say that this has been known for, n years where n is large. So this is the thing that we'll try to generalize for quantum doubles. There's a question, why ignore the horizontal edge z dagger that the plaquette operator has, just like the horizontal edge is x dagger and the vertex operator on the boundary. I don't think I can understand the question. Where would I be ignoring this?
Can you hear me?
Yeah.
So there's a vertex operator poly, right? So that's the boundary term.
Yeah, sorry, I'm still having trouble hearing you. Maybe we can chat after the talk. We can sign off and on, because I think you were fine before.
That sounds good.
Okay. Okay, so we're left with at the end the Ising/clock model, which I write here at the bottom, restricted to a particular sector of the symmetry that's represented by this global bulk star operator. That's the product of all x's on the spokes, which is the same as the product of all x operators at sites x over all x. So remember, we have yet to apply that. And the way you apply that here is just project this Ising model into a global symmetry sector represented by this global symmetry x global being 1. So the plaquette constraint, the star constraint becomes a global symmetry of your Ising, of the Ising or clock model that restricts you to a non-tensor product space, to a symmetry sector. The other symmetry sectors represent other excitations of the bulk. And we've worked out those details in an appendix of the paper. So that's sort of this extra ingredient that you have to take into account if you want to interpret the clock model as lying on the edge of a quantum double. Okay, so for quantum doubles, the procedure is pretty similar. You kind of just replace the operators with different, with their non-abelian counterparts. X dagger is replaced by x with arrow pointing left, and x is replaced with by x arrow pointing right. So I'll explain these right now. So now, instead of a Zn valued space at each site, we have a group valued space at each site. The group here is a finite group. And a group here, just to recall, has is under multiplication here. It has the properties of closure, the existence of an identity, and the existence of an inverse. And using these properties, you can define what's called a regular representation of X-type Pauli operators that act as permutations of your group valued kets, group labeled kets, that correspond to multiplying the group element representing the ket either from the left or from the right. Now, a group also has irreducible representations, or matrices that satisfy the multiplication rules of the group, namely the matrices I'll call here Z bar, or Z, I'll just call it Z, and these Z matrices evaluated at G and H and multiplied produce a Z matrix evaluated at the product of G and H. So these Z's are scalars if the group is abelian, but they can be matrices if the group is non-abelian. And they satisfy this first line. And then the second line they satisfy is if you tensor them together, so these matrices are labeled by the irrep index lambda. So lambda labels all the different irreducible representations. And if you tensor or fuse two different representations, you can express the result in a direct sum of the irreducible representations. And this is akin to your favorite quantum 1 homework assignment where you have the tensor spin 1/2 particles. You were doing irreps of SU2. You can do this for general non-abelian groups, even as finite ones or compact ones. So these irrep rules allow you to define Pauli Z-type operators that I'll call group valued operators, because they're basically diagonal matrices in the group space, where on each diagonal you have the particular irrep Z lambda evaluated at the corresponding group element that it's next to. Now, in general, because the group is non-abelian, these Z's lambdas are matrices. And so technically these Z hats live in a tensor product space where the first factor is the irrep space and the second factor is the group space. And so to obtain valid operators on the group space only, you have to take matrix elements of the Z lambda irreps or traces of them or something like that in order to remove or trace out the irrep space. Now, I'll omit from now on the direct product symbol here, but just want to make sure that we all keep in mind that these Z lambdas are matrices and we have to clothe them in a trace or take their matrix elements. And one kind of interesting connection between these operators that I seemingly cooked up out of nowhere is that they actually are discrete analogs of group valued fields from the nonlinear sigma model defined on a group, which is called the principal chiral model. So there are connections to field theories that we'll be utilizing using these operators. They also allow you to define fairly concise versions of the commutation relations that you ordinarily see for normal qubits and qubits. Namely the following: if you conjugate a Z by X's, then if you follow through the multiplication, you'll see that the Z hat is multiplied from the left by a matrix Z lambda. So this dot here is multiplication within the irrep space. And this is generalizing the phase relation that you get when you permute X and Z's for qubits. And you have two of them because you have two types of X-type operators, left and right multipliers. For example, so here I've picked the dihedral group Dn, which has two generating elements, a rotation R and a reflection P. P squared is identity and R to the n is identity. And these X operators are named merely just permutation matrix representations that satisfy the multiplication rules of the group. The irrep data of the dihedral group corresponds to the trivial irrep 1, the sign irrep 1 prime for odd n. So we'll keep with odd n for now on, and a whole bunch of two-dimensional irreducible representations that I've labeled by two subs with some subscript. And the irreducible representation matrices are as follows: for the one irrep, everything is just 1. For the 1 prime irrep, the reflection is a -1, and for the two-dimensional irrep 2 sub n, the rotation is this two-dimensional exponential of the Pauli matrix sigma z, and the reflection is the Pauli matrix sigma x. And so, for example, if you now put these inside the hat z operators and you apply z hat on a ket labeled by the rotation generator, you get this 2x2 matrix on the irrep space, which I'll denote by these square brackets. So this is sort of how this math goes. And if you apply this now and write the quantum double in terms of these operators, you also get a very similar structure as you did for the toric code in terms of the z's and x's. And similarly, you can apply this whole procedure that I explained for the toric code to the quantum double case. The stabilizer type math also works out if you're careful with the non-abelian nature of the z's. And what you get is in fact the flux ladder that Monk, Rasmussen, and Borello had introduced a few years back. You get a maybe slightly generalized version of it. So this connects the flux ladder explicitly to the quantum double bulk. And here I've kept things general by not yet defining the coefficient matrix C here that goes in, that lives in the EREP space labeled by lambda, and the scalars f sub h that multiply each X-type operator in the group. So once again, we have a global symmetry that this satisfies. The global symmetry is a tensor product of multiplications from the left, and it's satisfied for all values of the parameters C and F here, because namely the global multipliers from the left will insert, using the Weil commutation relations, will insert a Z H inverse and a ZH next to the respective Z hats at site X and X plus 1. And they insert them at the position such that the product is invariant. And so irrespective of the C matrix, this model has a G symmetry. And if you project the model into a collective Hilbert space where the global symmetry is 1, the trivial reducible representation of this global symmetry, then you can, that represents a edge theory for the quantum double model within the no bulk, assuming that the bulk has not been excited or does not have any anions in it. There's an alternative way of writing this that reveals a form for the capital C matrices that live in the EREP space. Namely, the capital C matrices are can be represented as this red thing at the bottom right. They're superpositions of the irreducible representation elements C lambda evaluated over all the group with some coefficients little c sub g, which are real. And the reason they're real is because the alternative expression for the two-body term is in terms of these projections, which are Hermitian. So the projections pi here project onto the product, the space, the subspace where the product of the inverse of the first group element and the second group element is K. So if you look at this projection, the way I've defined it, you'll see that H inverse times HK is just K. And these also span all diagonal two-body operators that commute with the global symmetry. And because they're Hermitian, their coefficients are real. And there's a Fourier type transform to go between the two forms. And so that pins down the form of the C lambda matrices. Okay, so I've taken a look at a general edge, but what's been studied in the literature a lot is gapped edges. And so if we do a sanity check, and we can specialize to the case of gapped edges, and those are defined and classified by a subgroup and its representation, which can be linear or projective. Now, I don't want to go into what a projective representation is because I'll only be using linear representations, but I think this can be straightforwardly extended to projective ones. But in any case, if you plug in the data used to define this gapped edge, then maybe the second equation here makes things look a little bit simpler. You just get a superposition of all these projectors, two-body projectors over the subgroup K, and a superposition of single-body multipliers over the subgroup K. And it turns out this is a frustration-free commuting projector model. And it's actually a simple model of symmetry breaking of G into K. If you further apply the global bulk, no bulk excitation constraint and project into the global symmetry sector where the global symmetry is 1, there's a unique ground state in that sector, and it's a GHZ type state that's a superposition of all of these states A capital K that I've defined over to the right here. And it's a superposition of all possible states like that. And these AK states are coset states because they are superposition of group elements in a coset of K in G. Cosets partition the group, so there's no redundancy or repetitions here. And this is the most general form of these sort of coset states. And if you know symmetry breaking, you will remember that the unbroken part actually lives in the quotient space. And so this is very much reminiscent of that. If you specialize to K being the identity group, then you get a massive GHZ state. If you specialize to K being the entire group, then the G mod K space is trivial. and you get a tensor product separable state where at each factor you get an equal superposition of all group elements. So this is encompassing sort of those special cases as well. And there's a notion of order disorder operators here. So I don't have time to get into that, but there's an old sort of notion of that from the clock model literature. And you can sort of do that here as well if you consider specific types of excitations that are coming from the bulk and touching the edge. So a single Z operator in the quantum double language can be interpreted as causing charge excitations labeled by the EREPs of the group. And I'm defining them in a language I'll relate to later here as gammas. And a string of X operators, which in normal language is a domain wall excitation on this symmetry breaking model. But in the terms of quantum doubles, it's actually something, it's a anionic excitation string that's coming in from the bulk, touching the edge at one point and carrying a flux labeled by the conjugacy class of the H group element. And this can be thought of as a disorder operator. And you can go through the motions here and figure out which of these operators excite the ground state, so take you out of the ground state subspace, and which do not. The ones that do not are said to condense, and the ones that do are said to become confined. And so for these simple cases that I've described, if K is just the whole group, then all of the fluxes leave the ground state invariant, and the charges give you local excitations and therefore become confined. But I want to avoid the exhaustive, anion classification and applying it to this model, so I'll move on, but just note that this can also be done. I'm going to move on to a general expression of the ribbon operators that live in the quantum double, and I'm going to apply the projection technique that we have to obtain flattened ribbons on this flux ladder edge theory. So Kitaev writes a form of the ribbon operator that one can manipulate to yield the following structure, namely a product of sort of alternating pi's and x's summed over all different ways to conjugate them. And notice the ribbon has a thickness in the bulk because the pi's and x's lie on different sites in the bulk. And what we obtain is, after applying this projection procedure that I outlined for the toric code, after applying a general version of it for quantum doubles, we apply a flattened version of the ribbon that is exclusively one-dimensional. So it's just depicted here on the right, and it's also a alternating product of pi's and x's, where the pi's are the two-body projections that I defined earlier, and the x's are the multipliers I defined earlier. And again, they're summed over various ways to conjugate them by group elements A and B, etc. So this operator behaves just as you would expect an anionic excitation to behave. Namely, it commutes with the flux ladder Hamiltonian at all sites within the body of the ribbon, which are all the sites Z that are between X and X plus Y. But it does not commute at the ends of the ribbon, which is site X and X plus site X plus Y, which are said to carry anionic excitations. And if you carefully look at all the different commutation relations with operators on the edge, you'll see that these flattened ribbons form the same quantum double algebra as bulk ribbons do, as revealed by Behe, Shor, and Whalen. I should have cited that paper. But basically, we get a 1D realization of this algebra. So we can use these ribbons and we can superimpose them and define Jordan-Wigner type operators. So this is just amounts to changing the basis. And the reason we change the basis is because we want to convert the two-body projections into products of ZZ effectively on the ends of the ribbon. So we'll obtain these lambdas that, for the abelian case here on the third line, are just products of x's with heads of Z dagger at site X and Z at site X plus Y. The second thing we do to obtain Jordan-Wigner type operators is we place one end far away from the chain. And that far away from the chain will just depict by site 0, that's outside of the chain. The chain starts at site 1. And then we further, to simplify the structure of these ribbons, because they're fairly complicated looking, you can, if you project the site 0 onto the identity state 1, you obtain the same order disorder operators that we had before. So these are much simpler versions of the ribbons that we defined, but nevertheless, it's kind of interesting that you can still obtain them by doing this procedure. And so now we have our Jordan-Wigner type operators that we obtained from ribbons via the procedure that I just mentioned. And we can express the Hamiltonian terms in terms of these operators. So the ZZ terms are just products of gammas, just like the ordinary Jordan-Wigner transform. The X terms are more difficult, but despite the difficult looking expression, it's actually only a 3-liner to show this, that you can also express the X operators as products, as 2-body gamma products. And if we apply this for the simple case of the dihedral group, there what we wind up getting is we can define a parafermion-like operator that I'll call eta, and a Majorana-like operator that I call gamma. So the parafermion to the nth power is identity. The gamma to the second to squared is identity. So they're in and of themselves, they have the same commutation relations as parafermions and Majoranas, but they do not commute with each other, and they generate the rest of these non-abelian Jordan-Wigner type modes that you can use to express the flux ladder. So just to summarize, there's various different types of anionic strings that we've introduced for this flux ladder. And the ones that lie, so the first type is ones that lie exclusively on the edge. And these are represented by these ribbon operators that lie on the space of the flux ladder. And then operators that come from the bulk and touch the edge in only one place are represented by these Jordan-Wigner strings that we can obtain from the ribbon operators by taking one end of the ribbon out of the space of the flux ladder and sort of simplifying it in the way that I described. So all of these behave very similarly. So these kind of, in the abelian case, they're kind of all more or less just products of X's. But in the non-abelian case, you see that the ribbons all have fairly different structures. So they're a lot richer construction here. Okay, so feel free to jump in with any questions. Guess I can do 20 minutes, 25 minutes or so to do the continuum constructions. So there's a well-known mapping of the clock model into an XY model that's pinned by a cosine potential. So we'll go through that now. If we take our clock model and we embed each point in the clock model, the Hilbert space at each point in the clock model, into a U1 rotor, we obtain the XY model, or the rotor model. And then if we further Taylor expand every operator in the rotor model by defining, by sort of, and take the continuum limit, then we obtain the free boson field theory, where the operators now, ZZ operator has become del phi and the X operator has become L squared. I think there's some questions.
Sorry, can I ask a quick question?
Sure.
So for the very simple case of toric code and its edge, we know that gapped boundaries of the toric code correspond to gapped phases of the Ising model, and a transition between them is described by some kind of electromagnetic self-dual boundary, right? Which is realized by the Ising CFT. And you can actually also kind of constrain the operator content of the Ising CFT by just looking at the toric code. So my question is, for these non-abelian generalizations of the 1D edges, gapped phases of these spin chains are, I guess, in one-to-one correspondence with gapped edges of some non-abelian quantum double. Right? What can you say about phase transitions between different gap phases? Can you constrain the operator algebra of operator content or the central charge or something of the transitions?
A good question. I haven't gone that route in general for general phase transitions. I will, in the continuum description, outline one particular critical point that you can have in the parameter space of these models. It's basically the same critical point you get in the clock model as well. And in that case, we are able to bosonize the corresponding continuum description. But other than that critical point, we have not looked at other critical points.
I see. Right, thanks.
So yeah, that's basically the other main result, and that's where I'm going to get to here. So if we do this following two-step procedure, we embed each site in a U1 valued degree of freedom, which allows us to express every operator as an exponential of the Lie algebra of the rotor, position and momentum operator phi and L respectively. We then effectively Taylor expand while taking the continuum limit. So we identify a difference of phi's at neighboring sites as a del phi operator. Then we get this free boson field theory. And here it is. So there's a ZZ term that's just del phi squared. There's an X term that's L squared. And then there's a pinning potential, a cosine pinning potential that remembers that you've come from a QDIT model that pins you to the n minima at each spatial point of the U1 valued field that correspond to the n states of the QNet. So this is the procedure we try to generalize to the non-abelian case. And the, in retrospect, simple idea here is to take the non-abelian group G and find a Lie group gamma that contains G. Now the Lie group we've picked to be sufficiently well behaved in the sense that it's compact because you can write the representations in a discrete way, and it's connected, which means you can represent everything in terms of the Lie algebra. And so we do that. Here in this table, I've wanted to depict it for the concrete case of G being the dihedral group and gamma being SO3. So on this third column, you have for the X type operators, SO3 involves the same type of rotations left and right as the dihedral group. It's just now there's sort of a continuum of them, and they're each expressible in terms of their corresponding generators, left and right angular momentum matrices. And you can naturally pick a subgroup of SO3 that's the dihedral group, and the X's are just the X's evaluated at that subgroup. Now the Z operators are based on irreducible representations, and there's an analogous picture of irreducible representations splitting off into irreducible representations of the dihedral group. So if you take an irrep of SO3, which is labeled by angular momentum L, and I've defined the matrix to be U here. So if you take an irrep U sub L of SO3, and you take and you evaluate it at values in the subgroup, in this case Dn, so R here is a rotation matrix that forms the group Dn, this irrep will branch or will be decomposable as a direct sum of irreps of the dihedral group, lambda. And depending on what L is, the various participating lambda will be different. But for every lambda, there's a corresponding L which contains lambda when you restrict it to the elements of the subgroup. And so in a dual way, you can embed the Z-type operators of the discrete group into Z-type operators of the continuous group. Moreover, because the continuous group in the non-abelian case splits off or branches into multiple different lambdas, you have a way you can use projections onto the irrep to select the different lambdas that you want. So in this case, this is a way to cook up the pinning potential that generalizes the cosine pinning potential. And here you project onto the trivial irrep of the group, which in the second step, here irrep 1, which is none other than +1. So you just get the trace of the projection itself. Well, the projection is onto a 1 E-rep, so you get just +1 at elements of the subgroup. And at any other element, you can show that you get less than +1 if you pick the right E-rep of the gamma group. So this is the sort of the group theoretic generalization to get these pinning potentials that will remember that you've come from a discrete space associated with a particular subgroup. So if we then do linearization, which is just, again, fancy form of Taylor expansion, we get this principal chiral model. It has a position, the ZZ term has become a position quadratic term that now has to be expressed in terms of the generators of the Lie algebra of gamma, which there are several. So I've suppressed the sum into summation here. The X operator has become a momentum current. It's also quadratic and also has a bunch of generators. And then, of course, you have this pinning potential where I've picked the ERF such that it's maximized only at elements of the subgroup G. The parameter matrices, again, are general enough to encompass different edges, as per the question, gapped or gapless. And the theory retains the G symmetry for all parameter matrices C and F, just like the lattice model. And the G symmetry here becomes just a global rotation, where now you have an integral and not a sum. Okay, so now we're going to take this principal chiral model and we're going to try to bosonize it. So first, to review the abelian case, coming back to the free boson can be recast as a quantum wire using something called Katz-Moody currents, which I'll define as JKM. So these JKMs at different points in space have the following commutation relation, where delta prime is derivative of the delta function in terms of X, and kappa is just some integer that people call the level. So these have a representation on both the bosonic and the fermionic side, which is quite remarkable. On the bosonic side, combinations of the free boson fields that we've discussed yield a representation of this current algebra. And the reason they do so is pretty easy to see. If you consider the canonical commutator between the two fields, e to the I phi and L, you just get a Dirac delta. And then you notice that the derivative of phi can be expressed in terms of e to the I phi, derivatives of e to the I phi. And if you do the commutator math here, you'll see that you obtain a derivative of the delta. So this is why these superpositions of the two fields satisfy the commutation relations of the Katz-Moody currents. But it turns out the same algebra can be realized using the following Dirac fermionic fields. If you just take products of two different fermion fields, psi plus and psi minus, you also get a representation of these Katz-Moody currents. And here you obtain the Dirac delta derivative by being careful with products of these fermionic operators in space-time. So a commutator has is a difference of products of psi x of y and psi y x. And if you write the products in this way that I've written at the bottom here, and are careful with the ordering of x and y, and take the limits as I've done here, you will see that you obtain the derivative of the Dirac delta function, which is called the Schwinger anomaly, I believe. But in any case, you have a representation of Km currents for both in terms of bosons and fermions. And so you can write the nonlinear sigma, sorry, the free boson part in terms of fermions and in what's called a quantum wire construction, which can then actually, one of the advantages is that it can be diagonalized using Fourier modes of the Katz-Moody currents. And so now what was done by Jason and Gill and others is that if you take this quantum wire and you impose different boundary conditions at each end of it, you will obtain continuum zero modes. So the left boundary condition pins the phi field to the subgroup Zn. And so there it pins you to a subspace that corresponds to the subgroup, the Q-net subgroup that we came from. And physically, this is associated with a ferromagnetic type of potential between the degrees of freedom making up the quantum wire. In the other case, in the dual case, the dual case winds up being equivalent to pinning the momentum field to the quotient space U1 mod Cn, whose states I've written at the bottom here. These are the same quotient states that I discussed in the symmetry breaking of the discrete case. Now, there's an extra wrinkle here, is that the field that's being pinned is not actually the momentum field at site at the end of the chain. It's a collective disorder type excitation, which people write as theta. But the math winds up being the same, and you're still pinning theta to a quotient space. So you can think in terms of group theory as the two regimes being dual to each other, in that one is pinning to a subgroup and the other is pinning to a quotient space. And this allows you to, at the very least, mathematically generalize this type of mechanism to these non-abelian principal chiral models. So that's what we do here. We're rewriting the principal chiral model. The quadratic parts can be recast as a set of coupled quantum wires using a non-abelian generalization of these Katz-Moody currents for gamma, which I won't get into, but it's kind of a similar but just more deep, more painful procedure. The derivative of the direct delta that's required for these commutation relations to hold is obtained in a similar way for the bosonic side and a similar way for the fermionic side. However, there's a caveat that, as opposed to the abelian case always working out for all values of C and F, this only works for a particular point C and F that corresponds to, on the lattice model side, a critical point. This is the critical point that I mentioned between sort of the all flux and the all charge edge that also exists for the clock model. It's sort of the simplest possible critical point you could think of. And this, I think, is the continuum analog of it. And you can write it because it's a critical point. It makes sense that you can write it in terms of some gapless theory. Now, the extra wrinkle you have to do for the non-abelian case is you have to further modify the commutation relation by adding, which is equivalent to having the phi and L fields as come from a Lagrangian that contains another term called a Wessamino-Witten term. So this, again, in the end, this just amounts to slightly modifying the commutation relations between the L fields. And if I'm extremely grateful for Fadiev and Takhtajan for the book that they wrote, because that very explicitly writes how to do that. It would not have been possible for me to understand any of this if it hadn't been for that book. Can't recommend it enough. But modulo this extra wrinkle of this extra term, you can write the principal chiral model in terms of a coupled set of quantum wires. And you can likewise consider pinning the two different ends of the principal chiral model to subgroups or quotient spaces associated with subgroups G or other subgroups associated with the gapped phases of the quantum double edges. And so we conjecture here that it may be possible that to derive non-abelian defects, that generalized parafermionic type defects for these types of Wessamino-Novikov-Witten quantum wires with different boundary conditions on each end. We haven't worked this out, but sort of what we've done is provide sort of a road going all the way from quantum double lattice models to fermionic field theories that at the very least at this critical point are fermionic field theories. And we outlined how to extend these superconducting ferromagnetic pinning mechanism to see if there's a way to obtain continuum zero modes in these field theories and thereby associate them with electronic systems. So that's basically it. So we develop here, coming back, we develop microscopic models for general defects that are strictly in 1D. We've tried to avoid sort of going to the category theory direction, working more on the microscopic level, keeping things general. More specifically, we've introduced these simplified 1D flattened ribbons that can be expressed in a strictly one-dimensional space, but still satisfy, as far as I can tell, the same algebra relations as the 2D ribbons. We've then mapped this Higgsing procedure to the non-abelian case and described all of its details thereby allowing one to obtain a continuum description of the flux ladder lattice model. And then at specific points, you can apply bosonization techniques to write the model in terms of fermions. And we conjecture there might be zero modes there if you're carefully pinning the different ends of this wire in different ways. One thing we have not done is considered string nets, which are even more general than quantum doubles. I've outlined order and disorder operators, connected them to quantum double excitations, and recast everything in terms of Jordan-Wigner, but it would be nice to strengthen the connection to order disorder operators and see what features of the abelian case translate to this non-abelian case. The techniques we use to peel off the edge have to do with sort of a generalization of stabilizer-based error correction. So it'd be nice to see how much of that mechanism can be further extended to these cases, which are not stabilizer-based models. And of course, we've discussed some Jordan-Wigner type operators, but that's not the end of the story here, because numerically studying whether zero modes coming from these operators are stable or not under perturbations is a very subtle issue. And this is something we have not done. And this is something that's on the to-do list as a result. And of course, we have only postulated continuum versions of these defects. It would be nice to actually develop them. And then furthermore, it would be nice to actually identify them with electronic physics, which we have not done. We've only done the math, the group theory extensions of these. We don't know, in some sense, what physical system those group theory extensions can connect to. And while the Wess-Zumino-Witten term that we've added in order to fermionize the field theory is allowed by the symmetry of the no bulk excitation constraint, it's not clear what relation it has to the original lattice model. It's possible that it may have some connections to gapped edges defined by projective representations, but it's not clear. So with that, I wanted to thank you for your patience and attention, and I hope that I got some of this very long project across. So thank you.
Thanks, Victor, for
I think it's still hard to hear you. If you could switch microphone, do you have another microphone? Yeah, and thank the 12 of you in particular for sticking around. This probably was a difficult talk. I guess, yeah, if there's any questions while Arpit sets up maybe another microphone.
Yeah, can you hear me now?
Yeah, I think so.
Oh, I see. Okay. Yeah, if there are any questions, please go ahead. And
you want to stop recording?
Yes.